Okay, hello to everybody. I'm going to talk to you about comets, how they can be connected to the origin of life. This will be focused mainly on the results we obtain on cometary samples that were brought back to Earth by the Stardust space mission, and also on another experiment that we are improving in our lab, which is DUSTER, which is collecting dust from the stratosphere. Let's see the outline of the lecture. I'm going to speak about the connection of comets and the origin of life, a theory that look at comets like objects that somehow participated to the process of the origin of life on Earth. And then we will see together from where cometary dust is coming from, and so why the connection can be considered among the origin of life and this object that can be primitive or primordial. We will look through this. Then we will speak about the Stardust space mission. There will be a short movie that will show you the scenario of this space mission. And then we will talk about the DUSTER experiment. And then just a slide to look into the future. We know that for the origin of life, there are three ingredients that had to be there when life started on Earth. These are water, organic molecules, and an energy source. With these three ingredients, one can go through the starting ingredients to the life, going on, let's say, following the experiment performed by Miller, that considered all the three ingredients being on the Earth when everything started. And then there is another theory that looks at these ingredients as coming not only from Earth but also from outside the Earth, so some extraterrestrial origin. And let's say the object that somehow brought these ingredients on Earth, some of these, were probably comets. Why? Because if we see the arrow of the times just in the bottom of the slide, we can see that there is some connection in time among, let's say, from the very beginning, Earth formation can be dated somehow 4.6 billion years ago. And then after after this period of planetary formation, there were a big instability, gravitational instability in the solar system. And so a lot of small bodies impacted on bigger planets. In particular, there was a maximum of this, how it's called, cometary bombardment, which is dated at about 3.9 billion years ago. And the oldest traces of life in rocks are dated among 3.8, 3.5 billion years ago. So the time connection among these two events and the maximum of cometary bombardment should have been a period very not so comfortable, let's say, for such a delicate process to be started. It brought scientists to think that there was maybe a connection among these two events. And let's see why comets among all the objects of the solar system, and from where cometary dust is coming from. Let's start from the very beginning. So 13 billion years ago, from the Big Bang, the universe formed. And then from dishomogeneities present at that moment, galaxies formed. And within each galaxy, I'm showing you a spiral galaxy here, which is similar to our galaxies. Within each galaxy, there are some regions that are formed by dust and gas. These are these dense molecular clouds that in which some primitive amorphous material is present. And this is the region where actually all the stars formed, and as the other stars, also our sun formed. In fact, in this very dense agglomerate of dust, the process of the star formation can occur. It starts and then it becomes like a protoplanetary nebula around the star, and the dust and the material surrounding the star is getting together, aggregating, forming planets. And just to be noted here that in these big molecular clouds, by infrared and astronomical radio and infrared astronomical observation, more than 150 types of organic molecules were detected. So let's see that already from here we start looking at one at least of the ingredients which is necessary for the beginning of life on Earth. And concerning comets, let's say the going from these molecular clouds, dense clouds, to solar system formation, somehow these organic molecules should have been there and remained there. And in particular, if we want to look for some very primordial material, we have to go at the very edge of the solar system, because there is the region which remain cold, and the bodies that form are quite small, so non-active. So they represent like a photograph of the condition we had at the very beginning of the solar system formation. So comets form, in fact, at the very edge of the solar system, and they can have a primitive component which is coming directly from the dense clouds, and they are surely primordial, formed by primordial material, where primordial, I mean the material that was present at the very beginning in the protosolar nebula, because they form at the edge of the solar system and they remain there, even if we will see later that Stardust results could tell us something a bit different from this after the cometary samples analysis. So Stardust. Stardust is a NASA mission that was designed to unreveal some secrets also about the connection of comets and the origin of life on Earth. I will now show you a movie which is giving you the scenario of the mission quite clearly. This is the target of the Stardust mission, and that was chosen also because it did not pass close to Earth until 1974. That it was the date when Jupiter's gravity changed its orbit. And because it has not been exposed to the Sun at close range, its composition has not been altered so much from its original condition. So material was primitive. And then by the time of the Stardust encounter, Commonwealth 2 made only 5 trips around the Sun. Okay, let's see the movie.
Stardust, bringing cosmic history to Earth. Comets are believed to be the most ancient objects in our solar system. Made of ice, dust, and carbon, these celestial beacons are thought to hold secrets to the early formation of the planets and the Sun. When far from the Sun, a comet's nucleus is cold and its material frozen solid. As the comet travels towards the Sun, the ice begins to warm and the materials begin to evaporate, forming an atmosphere called a coma, creating an enormous tail which fluoresces in sunlight. One of these cosmic interlopers, Comet Wild 2, was the destination for Stardust. NASA's Stardust mission is managed by the Jet Propulsion Laboratory in partnership with Lockheed Martin and the University of Washington. The ambitious goal of this mission is an historic journey that will bring back to Earth the first ever samples of a comet. This 850-pound spacecraft was launched on February 7, 1999, aboard a Boeing Delta II rocket from NASA's Kennedy Space Center at Cape Canaveral, Florida. After 5 years and 2.1 billion miles of travel, Stardust encountered Wild 2 on January 2, 2004. As Stardust neared the comet, the spacecraft deployed its collector grid to capture particles of the comet. This tennis racket-looking device contains over 100 ice cube-sized compartments filled with the world's lightest known material, a silicon-based substance called aerogel. These comet particles, moving at 6 times the speed of a bullet, collided with the aerogel. With a heavier substance, the comet particles would have vaporized. But the light aerogel served to slow down the particles, capturing for scientists these microscopic clues to the formation of the solar system. But catching the comet particles required more than aerogel. The spacecraft had to do its part to soften the blow of capture by lowering its speed at time of encounter. Still, Stardust was traveling 13,000 miles per hour when it passed through Wild 2's coma, coming within 149 miles of the comet's nucleus. At such close range, the possibility of a larger piece of the comet colliding with and destroying the spacecraft was a genuine concern. For protection, shields were installed on the front of Stardust. Like a battering ram, the spacecraft made its way safely through the coma. Shortly after encounter, the collector grid was stowed inside the sample return capsule for the 2-year journey back to Earth. Another mission objective was to take close-up images of Comet Wild 2. Using a camera similar to those on NASA's Voyager spacecraft, Stardust delighted scientists with spectacular images of the comet's surface and features. By the time Stardust returns to Earth, the spacecraft will have logged 2.9 billion miles on its 7-year journey. That will give Stardust the NASA record for the farthest distance traveled by a solar-powered spacecraft. As it nears home, Stardust will refine its flight path with a series of maneuvers. Once in the proper position, the spacecraft will release the sample return capsule with its precious cosmic cargo. The next stop is Utah. The capsule will plunge into the Earth's atmosphere at nearly 28,000 miles per hour, one of the fastest re-entries ever undertaken. The friction of re-entry will dramatically raise the temperature of the heat shield, creating a glow in the early morning western sky. 20 miles above sea level, a small drogue chute will deploy, further slowing the capsule. 6 minutes later, the main parachute deploys, carrying the sample return capsule to a soft landing within the Utah Test and Training Range. After recovering the capsule, the comet samples will be transported to NASA's Johnson Space Center in Houston, Texas, where scientists will first open this treasure trove of new information. NASA's Stardust mission, helping scientists to unlock the secrets of the early formation of the solar system and our Earth. By exploring comets, we will discover the mysteries of life and beyond, as only NASA can.
Okay, the panel that the Stardust spacecraft exposed to the coma of Comet Will 2 was made of many aerogel blocks. This is a very peculiar material, which has the lowest density, the lowest possible density for a solid material, and it was chosen and selected just to be able to stop the entrance of to stop the grains of the cometary dust, trying to modify the least as possible the cometary dust when entering at a velocity of 6 kilometers per second. So the material had to be low density, but as well had to stop the grain when entering in it. So this was the material chosen, and now we see the light track of the probe containing the cometary samples that was coming back to Earth and landed in the Utah desert. And here they are. They found the little capsule by helicopter, and the capsule was brought back to the Johnson Space Center, of course, in a clean room. In fact, contamination issue, as you can imagine, is very one have to take it in a big consideration just to avoid any contamination of the samples. And they opened the probe, and at the very first glance, they could see some of the grains that impacted in the aerogel and were trapped inside it. Here we see a block of this aerogel with the track in it. The grain was coming into the block from here, and it formed this type of track, which is enlarged, zoomed in on the right. And as you can see, this is what it was called a bulk track, which is formed probably by the grain that was containing quite a lot of volatile material. So when impacted the aerogel, it goes like blowing up, and the aerogel was modified, as you see here. And many tiny pieces of the particle can be found around all this track. And then at the very end, there is what is called the terminal particle. In this case, is about 50 microns. And what we saw with the analysis is that at the very end, the particle was composed mainly of minerals and not anymore of, for instance, carbonaceous material or the volatiles that were loosened at the very beginning of the track. This is one type of the track, but then we had actually many types that were formed in different shapes depending on the type of material that was the grain was composed of. In fact, if the material was mainly a mineral, then the track would have formed was something like this. It was called like a carrot-like, and no bulb at the very beginning of the track was present. Here, upright, you see different samples of particles that were collected at the very end of the track. So these were called terminal particles. After the Stardust samples came back to Earth, NASA gave these samples for the very preliminary analysis to about 200 researchers all over the world. And we started the investigation of the samples in a, let's say, closed phase of analysis, just to see the very preliminary results and to understand how these samples were formed and the composition, the morphology, depending on the technique that was applied. In particular, for what concerned our group, we asked for 7 grains that were extracted from one of these bulb tracks, the 35, and this was because we were, of course, interested very much in the analysis of the organic component of the cometary material. So this is the reason why we chosen a bulb track. And in fact, and then we applied 3 different techniques on the grains that we received by NASA. And the techniques are micro-infrared, micro-Raman spectroscopy, and field emission scanning electron microscopy with ADX analysis for chemical composition. Here I'm showing you also another track from which NASA extracted the grains from a second that assigned us after a second successful proposal presented by us. And then here is the third track for which actually in this case we asked for terminal particles. And I will show you the difference among these grains collected from different tracks. Here I'm showing you what we found with infrared spectroscopy on the particle extracted from the bulb track. And in fact, we could see from the infrared spectrum the GH bands testifying that organic molecules were present, and we could retrieve the ratio among CH2 and CH3 band, which give us an information on the shape and the characteristic of these molecules. And in fact, what we could conclude was that these molecules that we detected were actually similar to what was seen also in the diffuse interstellar medium, but the molecule were longer and less branched aliphatic chains. The ratio of CH2 and CH3 was similar to what we found in interplanetary dust particle, more than interstellar material. And this is one of the items that leads the preliminary examination team to conclude that in comets, the comets are mainly primordial and less primitive. So what is found actually is something which is close to the solar nebula, but not so much to the interstellar component. Then here I'm showing you what we got as an example, a field emission scanning electron microscope image of one of the particles up right. And in this case, it was quite interesting because from infrared spectroscopy, we could combine with scanning electron microscope EDX results, we could conclude that it was probable the presence in this grain of phyllosilicates containing calcium, aluminum, and sodium. And this is an important issue in support to the cometary aqueous alteration. Okay, here I'm showing you the grain of the second track I showed you at the very beginning, and just to let you understand how samples are prepared. Our techniques, the techniques that we applied, are non-destructive in this case, and the advantage is that after our technique are applied, then other scientists, other groups can apply further investigation with other techniques to know more about the same grain. And here you see in the dark spot here, this is an optical microscope attached to the infrared, micro-infrared spectroscopy. And here you see the white spot is the aerogel. Of course, when we were measuring the grain, we had to have something like a reference of the aerogel, which is, of course, unfortunately, giving a contribution to the measurement we performed on the grains, that everybody performed on the grains, because the aerogel had a lot of qualities, but it's true that somehow the grain were like contaminated by the presence of the aerogel, because the aerogel was not possible to be completely removed around the grain. And now here, this is the preparation, a bit different from the first two types of grains, of the grains extracted from the more carrot-like track. In this case, we analyzed two terminal particles, what we call here TP2 and TP3. You see the dimension were 11 microns in this case and 9 microns in this case. And what we decided to do, let's say, with the aim of get rid of as much as possible of the aerogel that was present around the grain, and also to let's say enlarge the dimension of the grain, the surface that we were looking at, we pressed this grain inside what is called a diamond cell. Two diamond cells, each grain in each diamond cell, and this allowed us, as you see here, to smash the grain and obtaining them with another shape, but the aerogel on top of the grain was a bit less, and also the surface that was flat with respect to the beam of our different analytical techniques was improved. And here are the results that we got with these other techniques. As I said, these are terminal particles. In fact, we expected not to find any organic component, and this is in fact confirmed. And we could reconstruct like a map of the grain, which is, here you have the legend. So you see that the calcium domain, which is this white spot here, could be interpreted as low calcium pyroxene or submicrometric inclusion of calcium-rich compound. And then the yellow domain is sulfur and nickel, and it's surely represented by iron nickel sulfide inclusions. And then there is the grid domains, which are composed of aluminum and sodium plus calcium domain that could be interpreted as a plagioclase or a melilite. Finally, there's a purple domain, which is surely olivine, and this is not, it is well expected to be founded on comets. And the empirical formula is shown here. And then again, for the second grain, we could reconstruct the composition by a combination of field emission scanning electron microscope and NDX analysis. And I have to say that all these results were somehow confirmed by the other two techniques, infrared spectroscopy and micro-Raman spectroscopy. Something more general, a result which is not coming from our group actually, it's by Elsila et al. 2009 in Meteoritic and Planetary Science paper. In this case, they got very nice results because they could detect actually the trace of glitting, which so are, let's say, they were, of course, they can illustrate that the potential delivery and survival of amino acids to the early Earth by comets. And then summarizing all the Stardust findings, not all, but main Stardust findings till now, we can say that the large, from 1 to 10 micron crystalline grains of phosphorite, enstatite, plagioclase, and iron nickel sulfides are common. Abundant high temperature minerals, andesite, diopside, spinel, etc. are present. Cometary grains are weakly constructed mixtures of subgrains of various sizes and compositions. And the 10% or possibly more of the comet's mass was transported somehow outward from the inner region to the edge of the solar nebula as particles larger than a micron. So this is a very nice result that improves the study on cometary formation. In fact, finding minerals that are high temperature minerals. This means that these minerals form like inside the orbit of Mercury, and then they were somehow ejected outside the solar system, at the edge of the solar system, where they aggregated to form the comet. So all this is testifying a huge mixing in the early solar nebula. As an example of one of the grains, I'm reporting here an 8 micron grain, which has 3 major components: the sulfate, pyrrhotite on the left, and then the 3 micron enstatite grain upper in the middle. And then the fine grains, here there is a mistake, of course, it's not millimeter, but it's micron. And then the fine grain porous aggregate material with chondritic elemental composition. So as you see, there is a very big dishomogeneity in one single grain of 8 micron in diameter. High oxygen and nitrogen contents, and also a high ratio of CH2 and CH3 indicate that WIL2 organics are not similar to those found in diffuse interstellar organics. WIL2 material is highly crystalline, structured rather than amorphous, and isotopic anomalies show the presence of pre-solar materials, but it is rare. So WILT 2 does not seem so primitive in the stellar, but rather primordial. So it's giving a picture of the solar nebula. Now, to resample with our mission, which are the advantages? Of course, we can use state-of-the-art analytical techniques that it's also improving year by year, but the samples are always there and available to be analyzed with improved analytical techniques. Resource for current and future studies by a broad community. Of course, the samples, as it happened for Stardust, can be distributed all around the world and studied by a very broad scientific community. The analyses are iterative and fully adaptive, so the results are not limited by instrument design or current scientific ideas. And it avoids limitation associated with spacecraft cost, power, and mass, because the measurement, the analysis are performed on Earth. Analysis can be replicated, verified with multiple techniques, and calibrated. And instrumentation, as I said, improves over time, so the samples can be reanalyzed. But it is also true that per 10 to the 4 tons per year interplanetary dust particles, mainly of cometary origin, fall on Earth. So collecting interplanetary dust particles in the Earth stratosphere is a very low-cost possibly cometary sample return mission. And in addition to this, there is in the stratosphere also a very, very rare and important component can be collected, which is the interstellar component, which is giving us a picture of could give us a picture of primitive material. And this component, as well as the interplanetary dust particle, can be collected in the stratosphere. In fact, the presence of interstellar material in Earth vicinity demonstrated by Ulysses, Cassini, and other interplanetary missions, and measuring the present composition, of course, would give indication on unaltered condition outside our planetary system. So with the aim of collecting dust, which can have also an interstellar component, in our university we developed DUSTER, which is dust from the upper stratosphere tracking experiment and retrial. And this is done in collaboration with the University of New Mexico, Professor Rick Meyer. And the responsible were previous principal investigator was Palumbo, and now the present principal investigator is Della Corte. And this instrument is devoted to, as I said, collecting dust in a size range between 0.1 and 10 microns. And this dust is collected in the Earth's upper stratosphere, and is compatible. The instrument is compatible. Let's say the design is compatible with the collection also of the interstellar component, and the operational cost, of course, it is quite low. And the management of following analytical work for the best data exploitation. The DUSTER flight campaigns were performed in Kiruna, Sweden in 2006, and then from Svalbard in Norway in June 2008, and then again from Svalbard in 2009, and then the last one was performed in Kiruna in 2011. And let's give a look to the flights performed. Of course, the first one was just a qualification flight, so I will not talk about that. But I will show you some results on the other 3 flights. The first one was a standalone flight, which started from, you see here the trajectory, started from Svalbard, went up to an altitude, the sampling altitude of 37 or 38 kilometers. And it sampled 6 meter cubes of air and collected dust on the ad hoc design substrate that I will show you later. And then another flight again from Svalbard. In this case was quite longer. It starts from Svalbard and then it was recovered in Baffin Island. And the sampled air volume was, in this case, 32 meter cube of air. And then finally, this is the last flight in 2011. It was performed at about a bit more of, it was 31 to 33 kilometer sampling altitude, and 3.6 meter cube of sample of air was sampled. Here again, just a glance to the first flight, which was not a scientific flight, but here I'm showing you what is very special of Stardust, which is the sample holder. The sample, to avoid contamination, as for Stardust, given by the mean of collection, we use this substrate that are very clean and very well, let's say we characterize the surface very well by scanning electron microscopy before flight, and then after flight we identify the particles really collected in the stratosphere that are not contaminated by any means, because there is no need of sticking material on them. So these substrates are directly, when the data is open in a clean room, then they are directly positioned in the apparatus where we have to perform the first analysis, which is scanning electron microscopy. Okay, here, just to show you for the results we obtain, this slide in the following ones, what we collected in the 2008 flight. Here an example of the particles typically collected. These are really very small particles. It's like 0.5 micron about, and also this is a very small one. And the nice thing in this case was that we could identify like a family of collected particles that was showing a similar composition, but a morphology very much, and structure very much differentiated. So in this case, I'm just giving you an example of the low resolution image and then the high resolution image. And in these two images are zoomed in some peculiar morphology present in this brain, and then the analysis to check for the composition. And as you can see, the calcium peak is very much it's important in this case. The content of calcium is quite high, and this as also in the other particles that were collected. So the interpretation of this collection of this let's say family was that it's like because of the different morphology we could observe these grains like this that are mainly minerals, but then some of these went through some kind of heating process, and then in this case these particles, so they were partly processed for this family here, and then in this case these are particles that from the morphology, one can conclude that they were condensed. So the material evaporated and then recondensing. From these chemical composition and morphology observation, we could conclude that that the particles were actually belonging to a unique body. It was like a fireball that entered the stratosphere, the terrestrial atmosphere, and then exploded somehow, and some of the material evaporated and recondensed, and some of the material remained instead unprocessed. And from the temperature and the composition and comparison with models, we could conclude that the body that entered into the Earth atmosphere was probably of cometary origin. Okay, let's go to the 2009 flight results. In this case, we were not so lucky. Here I'm showing you the collection chamber that is, of course, assembled inside a clean room. And then here is the launch of a very, very big balloon. In fact, in this case, Duster was not a standalone flight, but was mounted together a very big payload of some tons. And unfortunately, you see here the whole payload, and Duster was just on the top of this big payload. Here is the parachute after landing in Baffin Island, and you see here that Duster was not so in a good health when arrived back, because there was a delay in the recovery of the big payload because of the weather. Something happened to the batteries, lithium batteries of the main payload, and so the fire started on the big payload, and also there was like a shifting of the payload, and Duster went upside down, and it was like crashed by the big payload. But luckily, the chamber was still there and quite intact, apart from the fact that the valve had a leaking. So some of the materials that we found inside are like contamination. So we have to do a lot of big work to disentangle the stratospheric components from contamination. Here I'm showing you, this is a typical aggregate of smoke, condensed smoke due to the fire. Okay, let's go, let's shift this, and we will go to the Duster collection of 2011. In this case, it was a very short collection flight, but it was quite interesting because we could find this object that I'm showing you. That the analysis of the rest of the collection is still ongoing, but what we are quite interested in is in presence of this organic object. It should be like a virus. We have to go in depth to understand which type of virus is, but of course we have to perform a lot of, this is just a very preliminary result I'm showing you, but it is interesting that we could collect something of biological origin in the upper stratosphere, but we will go through this in more details in the future. Okay, so just to conclude now, let's give a look to the possible future extraterrestrial dust collection. This, we think, will contribute to clarify the origin of life on Earth. There will be a next Duster campaign in 2013 that will, we hope, collect interplanetary possibly, probably, hopefully, the interstellar dust that is coming through the atmosphere while Earth is moving through the galaxy. And then we have another mission, which is the NASA mission. It's not yet selected, actually, but this is planned to bring back dust from an asteroid. And so let's see how it will go, if it will proceed. Of course, it will be very interesting also to study material coming from an asteroid. Again, also from an astrobiological point of view. And then finally, we are also participating to a proposal which will be submitted to NASA in the future, that will again go on a comet and collect some sample and bring it back to Earth for further analysis from a different point. Okay, that's all I wanted to say. Thank you very much for your attention. And if there are questions, I'm ready to answer.